All right. Welcome, everyone. Welcome to hour 2 of Cruising the ML World with HPCC Systems. This is our second hour of our ECL workshop for the Community Day 2021. And as always, my name is Bob Foreman, and with me is my esteemed colleague and our machine learning coding expert, Hugo Watanuki. Both of us are senior software engineers, of course, at LexisNexis Risk Solutions, and also we are ECL trainers. So glad you could join us on our journey. I know that a lot of us have been sequestered at home because of all the times we've had in the last few months. So we want to have a nice journey through the machine learning world. And so let's buckle up and let's the journey begin. We'll go to our next slide, which starts with our travel quote of the day. Now, remember, we had a travel quote of the day yesterday, and we will have one in hour 3. Today's travel quote was from a famous actor named Sir Richard Burton, who said, "The gladdest moment in human life, methinks, is a departure into unknown lands." Today, our unknown lands are going to be linear regression and logistic regression. And also, remember the Mandalorian, who said, "This is the way." All right. So those are our travel quotes for the day. Let's go ahead and journey to our first land, which is the land of linear regression. And before that, real quickly, hour 1, we looked at unsupervised learning. In hour 2, we're going to be focusing on supervised learning, which means what it says. It requires a little more interactivity with the user. So the idea is to set parameters, let the computer learn, come back with its results. If we don't like the results, we can tweak the input parameters again, and so on and so on. So it's dependent on us. These learning methods are dependent on human intervention. Where unsupervised, we can set it up and then the computer goes, "Leave me alone. I'm going to learn on my own." We talked about that in yesterday's workshop. And tomorrow we're going to be looking at deep learning and ensemble learning. So strap yourself in. We're going to be looking at neural networks on hour 3, as well as an ensemble method, a special boosted reg forest that will also be presented. But today we're going to be focusing on our supervised learning. Here is, again, the graphic of some of the more popular machine learning methods that are available, the algorithms and so on. So for example, SVM, under supervised learning, is support vector machines. That's one of our other bundles that are available. But we're going to be going with what we like to call the low-hanging fruit. We're going to be starting with our discussion on linear regression at the bottom, and then we'll wrap up our hour 2 workshop with a discussion of logistic regression. Regression. What does that all mean? Let's look at it right now. So, as you watch this workshop, you're going to want to run the code that is available on GitHub. We'll send you that link, of course, at the end of this presentation. And of course, also then you're going to want to have the machine learning bundles installed. Once again, open source machine learning bundles that are available on hpccsystems.com. Now, like we talked about in yesterday's workshop, you're going to have your HPCC client tools installed on your system. And you can have multiple versions of the client tools. That's the beautiful thing about ECL and HPCC systems. The only thing I'd recommend to all of you is that you would install from the most recent version of your client tools. Some machine learning bundles will require a version 7 and greater or a version 6 and greater and so on. But I like to always recommend to people to install from the latest version. So from there, after that, and you've got Git for Windows installed. Now, yesterday, when we went through our hour 1 workshop, you should have already installed the ML Core. But once again, the 2 bundles that we're going to talk about today also require ML Core, as well as the Linear Algebra Parallel bundle, PB Blast. So once again, you'll have to have that installed in your bundle repository. And then finally, linear regression and logistic regression. So once again, you're going to open a command line window. You're going to navigate to your client tools bin folder, and then you're going to literally copy these script ECL bundle install and the name of the Git file and install your bundles. Once again, remember your command window must be run as an administrator. All right, so now let's talk about our first destination, the machine learning linear regression bundle. So a lot of data scientists, like my good friend Roger Dev, likes to call linear regression low-hanging fruit, or the hello world of machine learning algorithms. If you're getting into machine learning for the first time, it's not a bad bundle to start with, although I think I prefer learning trees better because learning trees is even easier to learn. But also the linear regression uses the same pattern that we talk about in all of our bundles. Namely, number one, the most important thing is to get your data ready for the model. Number two, then you're going to train the model. And then number three, you're going to predict the model. So linear regression, of course, is part of the supervised machine learning family. We already talked about that, and focuses on quantitative or the regression model. Yesterday, when we were introducing you to machine learning terminology and concepts, we had a quantitative method and we have a qualitative method, where quantitative is a scalar value like the price of a home, for example, where a qualitative method would be more of classification, like, is this image a dog or not, or is this particular customer going to come back based on the comments that he's given and based on his metrics? Do we think this customer is going to give us a call back, true or false, just a binary condition? All right. So interestingly enough, the term regression goes way back to the 1700s, where we had this gentleman that's named Sir Francis Galton, who had an idea that he said that he believed that children of taller people tended to be shorter than their parents. And as the lineage went on, that he said that the children tend to regress in height towards the mean height of their parents. Now, of course, because of the study of genetics, he was proven wrong as far as the biological theory, but his mathematical approach of the regression that he was using was sound and correct. And so that term kind of stuck around over all of these years, and then into the computer technology age, where we now talk about quantitative models as being regression. Okay. And then what about the word linear regression? Well, of course, linear is a straight line that is normally where the result of that line is a function of your independent inputs multiplied by some kind of a coefficient, or think of it as an influence on that particular field value, giving us a final result. But again, a linear model being referencing that one predictive variable will be directly proportional to the predicted outcome. And so here we go back to, well, I had to kind of really go back in time here, but I used to love math. I always loved math when I was in high school. And one of my favorite parts was geometry. And we started talking about the slope of a line. And of course, when I first started reading linear regression, I saw this equation here, y equals mx plus b, it all came back to me. So what does this mean, though, in machine learning terms? Well, y is our dependent variable, or the variable we're trying to predict. Of course, x is your independent variable in a two-dimensional x and y, but of course we have support for multiple independent variables. But the variable we're using to make the predictions, m is the slope of the regression line, which represents the effect x has on y. For in other words, if x increases by 1, y will increase by exactly m units, whatever that number m may be. So in linear regression, we're essentially mapping data points, those blue dots that you see on the right side on the graph, and then drawing a line through those cluster of points that best represents the least amount of distance between the lines and the points. Of course, I'm going to mention this again, but most real-world relationships are not linear. But if you have a linear relationship between an independent variable, independent field, and a dependent field, then linear regression is a good model to test. However, which linear regression model, if you go and research on the web, you'll see that we've got multiple versions of linear regression. And the one that we're choosing, the one that first came off the assembly line way back in 2012, when we first went open source in 2011, and then in 2012 we said, okay, we released our first beta version of our machine learning libraries, and we this was one of the first bundles ever released, linear regression. And of course, the most popular, one of the more popular linear regression algorithms to use is called ordinary least squares, or OLS. And again, the idea behind this is it takes the sum of the square differences between the observed and the predicted values, the observed values being the independent variables and the predicted value being our dependent variables. Minimizing it using this mathematical technique leads to less errors in the X and Y relationship, a smoother line, a smaller distance between the points in the line to help eliminate outliers. So we're going to be using the ordinary least squares method, which is the one available in our ECL linear regression bundle. All right, so now I'm going to run through the libraries real quick, but more so I'm going to save time for Hugo to come on. I just lost my clock here. There we go. I'm back. Sorry about that. So I'm going to go through these functions very quickly. OLS, of course, is the main module where all the magic happens, ordinary least squares. And this is what we'll use to start the training of the model. Once we've trained the model, we'll then get that model as a definition that will then be used in a variety of different measurement sequences. For example, there's the more popular one here is called betas, which is the degree of change in the outcome variable for every 1 unit of change in your predictor variables. All right, so the idea about this is the higher the absolute value of the betas, the stronger that independent variable influences the dependent variable. So I believe Hugo will be showing you that. Of course, the third part of any machine learning part is to actually test it. And so we have a predict function that allows us to send test data to our model. All right. And then we have an R squared value followed by the adjusted R squared value, which is our two more metrics that we use to measure the goodness of fit of the model itself. And then we have something called ANOVA, which is analysis of variance. And there's a whole bunch of stuff that's returned by ANOVA that we don't have time to cover, but it's just very well documented in the OLS module. We've got things like sum of squares variance, degrees of freedom in your data or your model, how much error you have. So all of this is just, again, the effectiveness of the model that you ran on your training data. All right, in addition, we have the standard error of regression coefficients. So this is the average distance that the observed values fall from the regression line. And using standard error and using the coefficients, we then start to mathematically manipulate different types of statistics. Like here, this one's called the t-stat, which is nothing more than dividing the value of the coefficient by the standard error. Then we have the Akaike information criteria, which again is a more detailed report on the goodness of fit of the linear regression model. P-value, which is our predictive value. All right, what does that mean? A low p-value will provide evidence that at least one of your coefficients, one of your independent variables is significant in determining your output. A high p-value would indicate that all of your values should in fact be 0, which would imply that the regression has no statistically significant predictive power. Okay, and then we have something called confidence influence or confidence interval. Sorry about that. And so confidence interval is, well, how well did the model perform again? And we have this thing called F-test, which is similar to t-test, where the t-test or the t-stat up above is for individual field values and their significance, where the F-test is kind of a summary of the entire significance of the entire model. So the F-test and t-test are similar, except t-test is for individual coefficients, where the F-test is used to test the entire regression. All right, so that brings me to our fun part of our workshop, the linear regression demo. So I'm going to stop sharing my screen right now, and I'm going to bring on Hugo, who's going to walk you through setting up the data, training the model, and then how do we analyze our linear regression model? So let me stop sharing right here and go ahead, Hugo, take it away.
Thank you so much, Bob. And before I start here, just want to remind everyone, if you have any questions during the presentation, feel free to post the question in the chat. Myself or Bob will promptly reply to you. Now, so welcome everyone for this first tutorial on today's session. For this first tutorial, I will be covering linear regression. So we'll try to apply some of the concepts that Bob has just presented, but in a practical or real life situation, trying to address a problem. But before we start, just want to quickly double check with you, you have all assets in place. And here on my screen, I'm sharing the code examples that we will be using today for our 2 linear regression. If you haven't already done so, remember to download the code examples from our GitHub repository. And last but not least, remember to make sure you have the machine learning bundles properly installed on your PC. And here today we will need the linear regression, logistic regression, but also the ML Core and the PBBLAST bundles as prerequisites. Okay, so getting started here, what the goal of this tutorial will be to actually leverage a property data set that I'm showing here on my screen, which contains attributes from properties. And we will try to predict or train a model using linear regression that can actually give us a prediction of the property prices. So in this data set, each record represents a property, and you have several attributes such as the house number, the street where the property is located, and you also have some more granular attributes such as the number of bedrooms, the living square feet, and so forth. So we'll take all this data, we'll assume initially that these attributes share a linear relationship with the total value of those properties, and we will try to train a model using the linear regression bundle. Okay, so first things first, we need to look at this data set and select the fields that we are going to work with. So if we open our file property ECL file here, you will notice we have our original record structure for the property data set, and we have a mixture of string and numeric fields. And since we are using regression, as Bob has very well emphasized it, and in order to make things simpler for us in a first step, we will just select the numeric field types and take them forward for our machine learning activity. So here at the bottom, I have the machine learning record structure that we are taking forward for this exercise or for this tutorial. And you can see we are either using unsigned 2 or unsigned 4 value types. Okay. Very well. Now that I know the field type, the fields that I want to use for my machine learning, I need to prepare the record set accordingly. And that's why we have the prep01 ECL file. On the prep01 ECL file, we have a similar module that we exercised on yesterday's tutorial. So here, besides adding a random number to shuffle the data we are using to train the model, I'm also cleaning up the data set to make sure I am filtering out every empty or 0 values for key attributes of the properties. And after projecting the filtered property data set into the machine learning record structure and sorting the data using the random number, I guess the most interesting portion or the new element that we are seeing here in this first tutorial is that I'm not only extracting the training data, the first 5,000 records to be my training data, but I'm also extracting the next 2,000 records to be my test data. And that's a possibility now because we are using a supervised learning method. So I do have the target values that I want my model to predict. So I can use those target values to train my model, and afterwards using a test sample to validate the quality of my model. And we are using here 5,000, 2,000 records as a starting point. You might want to use something different depending on the level of the amount of data that you have, you usually have a suggestion of using 70 to 30% ratio between train and test data. If you want to look how your data looks like after cleaning out and extracting the training and test samples, go back to your BWR, and you can see here, this is my trained data. I'm only selecting the numeric fields as I mentioned before. And here on the far right, we have the total value of the properties that we are trying to predict, 5,000 records, and the same thing for test data, 2,000 records. Okay, but as you might recall, the format or the layout we are looking at the screen right now is not actually what the machine learning data frame is expecting in order to train the model. So we still need to convert this record set into the machine learning data frame. And that's why we have the convert02 ECL file. In the convert02 ECL file, we will leverage the machine learning core bundle to help us with pre-processing the data accordingly. So in the first step here, we are adding a sequential ID field into our training and test data. This is a requirement as usual for our machine learning bundles. And I'm also using the toField function to make the conversion of my training and test record sets into the machine learning data frame. And this is similar to what we did yesterday, but I think, again, the most interesting part here are the extraction that we are making upfront, selecting the independent training records and the dependent training records. Remember, we are still dealing with a supervised learning method. So now I have the capability of informing the machine learning bundle which records correspond to my predictors or independent variables, and which records correspond to my target values or my dependent variables. And I can do this, I can use the same approach for my training data and for my test data. So that's what this convert02 module is doing right now. And if you are interested to see how does the machine learning data frame looks like after splitting the independent and the dependent test records, go back to your BWR file. And here we have the independent training records. You can see that for each property, I have the 8 attributes that we are using as predictors and the respective values of each predictor. If I'm not mistaken, this is the assessed value of the property, the year the property was acquired, the number of bedrooms, and so forth. Now, in the other record set, you actually have the dependent variables. And here you can see for each property, I have the total value of that property. So I'm using that as my target value to train the model, and afterwards we will use the target value to assess the quality of the model that was trained. Okay, so now that I have all my data ready and set to go, let's train the model using the train03 ECL file. And here I'm starting with importing the linear regression bundle as a starting point. And I'm also renaming my independent and dependent training data and test data just to make simpler for us to look at the code. So I'm going back to math here and just referencing my independent data as X-train and my dependent data as Y-train. And the same thing for the test data. Okay. The core part here is to make sure you select your learner. So like Bob has mentioned, we are using linear regression ordinary least squares for this particular tutorial. And I'm passing here my X train and my Y train so my learner can actually use this data to learn. And the get model function is actually the function provided by the bundle that will be able to extract your training model. And I'm also using the betas function right here just to show us how the beta coefficients look like after the model has been trained. Okay. Now, once I have my model trained, I can also use the predict function provided by the bundle, and by passing the X test records now, so my test data set containing the independent variables and passing the trained model, I can finally get my predicted values. And by using the predicted values and comparing them against my test data set, I can extract coefficients that will tell me or give me an idea of how good my model is. In this case, I opted to use the R-square and the adjusted R-square coefficients, which, like Bob has explained, will give me an initial idea of how much predictive power my model has. Okay, so if we look at the results here, let's take a look real quick. Here I have the beta values, and they are not standardized, as you will see. I have the predicted values for the property prices, the predicted prices for each property, and my R-square and my adjusted R-square values of 0.887, which again ties back with the predicted power of my model. Now, you might be wondering, what if I'm not satisfied with the quality of my model at this point in time? That's when you can also leverage the several coefficients that are provided by the linear regression bundle and make an optimization of your model. Here, I'm just selecting the p-values as a starting point, and we can look at the p-values of the coefficients and have an idea of which coefficients are actually not making a contribution to my model. So if we look at the p-values tab here, we could initially look at all the values below, for instance, 5% of a significance level, and consider those coefficients to be extracted from my trained model. So here, for instance, coefficient 1, 3, and 8 could be good candidates to be eliminated in the next optimized version of this linear regression model that we just trained. Okay, so that's it, folks, for the first tutorial. I hope you have enjoyed this tutorial, and I will now hand over back to Bob, but I will be back afterwards with the logistic regression bundle once again. So Bob, I will stop sharing my screen and hand over the control to you.
All right, thank you, Hugo. All right, welcome back. Great presentation again. I really loved it. Again, very clear, that simplicity of it. And also notice when you download the code of the different comments that are part of the code itself, so that if you want to know, like, for example, I might not remember what the confidence interval means. And so by putting comments in there, you can look at your code and say, okay, this is the values that I'm looking for. So, there's just so many analysis tools that sometimes you can get them mixed up. So commenting your code is kind of a very, good best practice to use, especially when you're learning these machine models and developing your models for the first time. So in summary, the advantages of linear regression, before we move on to the next travel journey, linear regression, it's simple to implement, as you could see. It's easier to interpret the output coefficients. Yeah, that's just a quantitative value. So you can, the higher the number or lower the value will give you an indication on how the model is behaving. It's the best algorithm to use when you know the relationship is linear. All right. So overfitting can be avoided using like Hugo demonstrated, the smaller number of independent variables and then cross-validation analysis there. Of course, the disadvantages is outliers can have a huge effect on the regression, can skew the line a lot. So you have to make sure that your outliers get either filtered out, or you just, I guess that's the best way to do it. And then, of course, the linear relationship between dependent and independence. A lot of real world applications just don't apply for that. So once again, in summary, it's a great tool to analyze the relationships among the variables, but it isn't recommended for most practical applications because it oversimplifies real world problems by assuming a linear relationship among the variables. But if you do have a linear relationship, then of course, linear regression is the way to go. All right, well, let's pack up again. Let us move to our next land of machine learning. And the next land that we're going to visit is called logistic regression. So I'm starting to sound like Rick Steves now. Some of you guys know who that is. So here we go, our logistic regression land. We, first of all, left the land of linear regression. And so there's a graph that was shown on previous slides. So now let's bring in logistic regression and talk about why they're talked about together and how they're related. They're both supervised learning, of course. And of course, logistic regression, unlike linear regression, is a classification model or a classification algorithm. And we are going to be using the binomial classification, meaning either true or false. And there are other types of logistic regression that, of course, Lily Zhu presented back on Monday at our community day. So she talked about some new and exciting changes to logistic regression. We're going to just talk about the ones that have been in place for several years now and how to leverage that logistic regression model over others. So essentially what happens, and why are these two close together and why are they related? And why is this thing called regression when it's a classification model? Well, the idea behind it is logistic regression actually takes the algorithm of linear regression and then filters it or sifts it through a sigmoid function. So the output of the sigmoid function, as you can see here, you've got an upper part of the curve shown at the top here. You've got a lower part of the curve shown here. And then you've got this scaling up and down. So you could look at it that way and say, well, if my values tends to hit this point right here, you have some kind of a threshold that says anything above this point will be considered true. Anything below this point can be considered false or zero. All right, so the sigmoid, a perfect sigmoid function in the perfect world would be a flat line here, and then almost a vertical line here, and then a line up at the top. So almost like a square wave instead of a curved wave or sine wave. Okay, so that's logistic regression. Logistic regression, because of the nature of how the independent variables are processed, it then results in a two-state condition. Now, in multinomial, you'll see multiple levels here, but this one for binomial is simple to analyze and look at because we have a lower and we have an upper window. All right, so the characteristics of logistic regression are interesting. Of course, they're used to predict the probability of something being either true or false, all right? And we're going to be using a different data set to demonstrate that. It relies a lot on normality. What does that mean in machine learning? Well, normality means that you should make your data roughly fit a bell curve shape before running certain statistical tests. So we don't like to have skew, especially when we're running training data, logistic regression. If we have more that are skewed positive, then maybe it's not the best way to evaluate or predict the model or classify the model. And in binomial logistic regression, the dependent variable is binary, meaning true or one or false or zero. More accurate for larger samples. Give me more data. I am HPCC. I would like more data. The more data, the better my result will be for logistic regression. Again, I mentioned it's a sigmoid function, and by tomorrow in our hour 3, we're going to talk about also another sigmoid being used in neural networks. So sigmoid is also a popular method when you're using classification in deep learning neural networks. All right, where do you see logistic regression used? A lot of, in my research, it looked like a lot of people in the medical field were using it, predicting how a particular drug affects a group of patients. So based on a number of independent variables coming in, that we could say this drug is effective or this drug is not effective, or they would have maybe a tendency to be addictive or maybe not addictive, and so on based on their characteristics. So it's used, logistic regression is used extensively in the medical field. And finally, the regression model allows us to establish a relationship between the binary outcome and the group of predictor variables. All right, so now let's dive into the regression library. Again, just like linear regression, using OLS. In this example here, we'll start by creating the model using binomial logistic regression. Then once again, we have a function here called get model that will actually allow us to grab the model so that we can use it in reports and we can use it in the prediction function of logistic regression, which we call classification. All right, in addition, then we have some other tools like binomial confusion. And binomial confusion is actually measures the performance of the classifier to check the efficiency and precision in predicting results. In a binary world, you have essentially 4 states. You've got, first of all, true positive, which means that the actual and predicted values were both positive. True negative, which meant that the actual value and the predicted value were both negative. And then false positive means that the actual value was negative, but then we predicted it as a positive. And then false negative is the actual value was positive, and then we predicted it as a negative. So that's what we are referring to here when we're talking about confusion and binomial confusion. We have a data stats evaluation that produces summary information about your independent and dependent fields. Handy thing to use. We have something called deviance analysis, which compares a proposed model with another base model. So using deviance analysis, you can see how does this new model behave with the older model. And once again, the beautiful thing about these particular bundles is, yes, you can archive and save these models and then use them again, call them back up, and use them to compare with new models that you're building. All right, so we've got deviance analysis. We've got deviance, the details similar to the analysis of variance, the ANOVA stuff, but adapted to the logistic model. And then one of the more popular ones is extract beta. Hugo's going to show you the extract beta. It's the coefficient weights and then the standard error that's displayed for each field. All right, so our last thing here, a couple of extract betas with different options, like extract the beta, but also add the confidence intervals in my model data set. Give me everything. I want to see everything, including the confidence intervals and the Z and the other p-scores and stuff. There's the p-value, the predictive model. And then there's another full report that you can run. We have the logic predict, which is a special function that you could use that some mathematicians like to use that particular prediction result. It kind of flattens it out and makes it a little bit more accurate. So you can try that out, the logic score in addition. And then Lucy, for some of you not part of LexisNexis that are watching this workshop, Lucy is a LexisNexis product. The acronym means, and I'm apologize if I'm wrong, but it's LexisNexis Ultimate Code Integrator. And so it helps to develop best practices and standards in all of our products. And so you could use logistic regression to generate a Lucy model to use where needed in any particular discipline or any one of our products that we're working with. All right, so then we have deviance information from a model that's analogous to ANOVA. And then we have our full model report, less the confidence information, and something called null deviance, which returns the deviance information for the null model. All right, so that's all the stuff again. You'll notice because these were like the first bundles that came out, we came out with all kinds of ways of measuring their effectiveness and statistics and so on. So now let's actually put it into a real world situation. And my colleague Hugo found this data set, and I thought it was really nice, remarkable. And of course, though, when you see banking, it's not like a bank, like a money bank. This is a phone bank that we're going to be referring to. So this is a data set that Hugo's going to introduce to you that talks about direct marketing campaigns, particularly of a Portuguese banking institution. And the classification goal is to predict whether the client will subscribe or not subscribe to a term deposit. And so there is actually the website that you can go to get that data. It's there's no personal information here. It's mostly numeric information. Well, it didn't start as numeric information. Hugo's going to show you that. So we had to do a bit of ETL to get it to the machine language format. And well, I'm just going to go ahead and present and let Hugo take it away from this point. So let me go ahead and stop sharing my screen. And Hugo, you have the floor, sir.
Thank you so much, Bob. And I should mention, I was really upset with this data set because the content was not in Portuguese at all. So, okay, so welcome back, everyone. So for the first or the second tutorial of today's session, I will be exercising some of the concepts around logistic regression that Bob has just presented, but again, trying to bring those concepts into a real life situation. And here on my screen, I'm sharing the data set that we are going to use. Like Bob mentioned, is a data set coming from a phone bank company, a Portuguese phone bank company. And on each record here, you actually have a customer from that company, and you have several attributes for that customer, such as the job, the marital status, the education level for that customer. As you might notice, those are not numeric at all. And at the far right here, we have a field that tells us if that customer actually, at the end of this marketing campaign, subscribed to a term deposit with this bank. So 0 means no, 1 means yes, okay? And we will try to predict by learning from this data set whether or not there are attributes from the customer that can give us a predictive power to actually understand if the customer will, at the end of the marketing campaign, subscribe for a term deposit. Okay, so first things first, I need to decide and treat all these customer attributes accordingly for my machine learning activities. And that's why we start with the file banking ECL file. Just like Bob introduced it, all these attributes were originally categorized as strings, and we then splitted those fields into fields that actually represent or have a quantitative meaning, such as age, duration, campaign, or prices indexes. But we also have a lot of qualitative attributes, such as the marital status and the education status. These attributes were originally strings, as you might have noticed, and for converting them into numeric values, we actually need to start an activity called encoding, where we'll transform the strings or translate the strings into actually categorical numbers. And that's why we have here our prep01 file, which looks like a little bit different from the previous prep1 files we have been using so far, because on this data set specifically, we had to not only add a random number to shuffle the data, but we also had to cast most of the attributes to a numeric value type, either unsigned, integer, or decimal values. Now, the more complex or the troublesome part, if you will, was to converting the qualitative attributes into numeric fields. And here Bob has come up with a very nice idea of using a data dictionary. So that's why we have this DCT's ECL file provided in this tutorial, because we are basically leveraging the data dictionary capabilities provided by ECL, and we are labeling each of the educational levels. For instance, if you have an university degree or high school, and we are labeling those attributes with specific positive numbers. So by the time we apply the data dictionary as a function for those categorical attributes, we end up with numbers that actually translate the original categories that the field or the attribute originally meant to provide. Okay, so that was the, I guess, the most cumbersome part of the ETL. And here I have all the dictionary declarations and the functions that we use to convert each of those strings into numeric values, or encoding, if you will. Okay, now if you want to take a look at how the data looks like after doing the preparation, just go back to your BWR file. And here you have your training data and your test data. Again, we are under the domain of a supervised learning bundle. So we have the capability of splitting our raw data set into a trained sample and a test sample. And here I'm showing you the trained sample with all the data already converted into a numeric value. Of course, age, duration, campaign were already numeric, but you can see here that marital code, education code are all encoded into their respective category. And at the end here, of course, our dependent variable or label that we want to predict. 5,000 records for training, 2,000 records for testing, okay? But again, this is still not aligned with the machine learning data frame format that we need to feed the algorithm. That's why we have, and it might be common for you now to think, we always have a converter to ECL file to help us with that task. Again, machine learning core will help us pre-process the data with the to-field function. And the only thing I want to call your attention here is that, of course, we need to adjust the number of attributes we are using here in comparison to the linear regression tutorial. We have here 20 attributes we are actually taking into consideration for this model. It was an initial assumption that we made. And the second thing I want to emphasize is that the dependent variable, we are actually using a very specific format. Remember, this is a classification method. So we are trying to predict a dependent variable, which is actually a label, a binomial label. So instead of using real numbers, real type numbers, we are actually using unsigned or integer values, okay? And if you want to see how the machine learning data frame looks like, just go back to your BWR file, and there you go. For my training data set, I have here a single customer ID and all the attributes of that customers that we're taking into the logistic regression algorithm and the respective value for each of those attributes. Remember, I think this is the age of the customer. And if you look at the dependent training records, of course, for each customer, you only have one dependent variable, and that variable is actually a label. You can see here, it is not a floating point number, it is an integer or an unsigned value type. Okay, so that's all the ETL we had to do here. We have the data ready and set for our logistic regression bundle. So that's when we should be opening up our train03 ECL file. And just like we did with linear regression, I make sure I import my logistic regression bundle as a starting point, rename my independent and dependent training and test data just to make the code simpler and to look more human readable. But the important part is actually here. I'm now selecting my learner as logistic regression, binomial logistic regression. I'm using binomial because remember, my dependent variable only has two possible values, 0, 1, so only two labels. That's why I'm using binomial logistic regression. And once I select my learner, I can use the get model function, which is usually provided with all the machine learning bundles, and pass my X train and Y train so my model can get trained. After my model is trained, I now can use the classify function provided by the bundle, and by passing the model along with the X test records, I can finally get my predicted labels. And by using the predicted labels, I can compare them against the real labels from my test data set and extract the confusion matrix, just like Bob has presented in his slides. And I'm looking at both the confusion matrix and the binomial confusion values, just as two quick coefficients for us to have an idea of quality from our trained model. So let's take a look at how those results look like. First, I have my predicted values, and you can see here for each customer from my test data sample, I have the value that was predicted for the label. Remember, only 1 or 0. But the most interesting result is actually on the confusion matrix. Remember, we were playing with 2,000 records as our test sample, and if you sum up the values here, you will end up reaching those 2,000 records. But out of those 2,000 records, 1,728 records were actually true positives. The actual class was 0 and the predicted class was 0. So our model behaved pretty well on that aspect. And I also have 84 records which were true negatives, or actually predicting that the actual class was 0 when it was actually 0. Now, there are two values here that you need to take into consideration, because 45 records were actually 0 on the test sample, but my model predicted as 1. So those are false positives. And 143 records were actually 1 on the original test sample, but my model predicted as 0. So those are false negatives. You need to take into consideration those values, because depending on how much quality or accuracy you need, you might need to optimize the model. And last but not least, in terms of assessment, if you take all those values from the confusion matrix and combine them into a single coefficient, you might want to look at the accuracy level here, and we reached something around 0.906. That, of course, depending on your area or domain of work, it might be appropriate or not. Finally, you might be thinking, what happens if I'm not satisfied with the quality of my model? Are there any options I can use to optimize the model? And just like we saw on Bob's slides, there are several coefficients we can look at, but I will just select one that I find particularly appropriate for logistic regression. It is the Akaike Information Criterion, or AIC. And that's a very interesting criterion because it takes into consideration how much deviance your model has, the lesser the better, and how many attributes you're actually putting into your model, the lesser the better as well, because you have a more parsimonious model. And the goal here is to always get the lowest AIC value. And if we look into our trained model, we have here a AIC value of approximately 896, but we are using 21 attributes. The 21st attribute is actually the value being predicted. But from this point onwards, one interesting thing you can do is to actually start your logistic regression, including one attribute at a time, and always selecting the attribute with the lowest AIC value. So if you go in a stepwise fashion, adding one attribute at a time, at the end of the process, you will get your model with the lowest AIC value possible, and then you have your optimized model. So this is just one of the possibilities you can start using with the logistic regression bundle. So that's it for the second tutorial, everyone. I hope you have enjoyed it. I certainly like it presenting this to you. And I just want you to remember, we were just scratching the surface here with these two tutorials. If you want to learn more about either linear or logistic regression, remember under your bundles folder, you have the linear and logistic regression folders that you can explore and obtain some more demos and training code that you can explore. Okay, so just wanted to make sure you have that in mind before we end these two tutorials. So now I'm done with the tutorial and I will hand over back to Bob, so Bob can wrap up with some of the advantage and disadvantages from logistic regression. So I'll stop sharing my screen here, Bob, so you can take over.
Thank you, Hugo. Wonderful presentation, well explained. And I forgot all the work that we did prepping that data, but it was a lot of fun watching that. That was good, and good use of the dictionary statement. When I saw that, my ears perked up because I've always wanted to use something practical for dictionary when that first was introduced, and it became a great solution. All right, so to wrap this up, people, again, the sun is setting and our ship has to pull back into port, so we get ready for hour number 3 tomorrow. So in summary, let's just review logistic regression as advantages. Well, once again, it's mathematically efficient and very straightforward. It's simple to implement, as Hugo demonstrated. It's pretty easy to analyze once you see a number of examples and the numbers that you're looking for. Again, widely used in machine learning, one of the more popular bundles to get started with, especially with classification. Of course, disadvantages, it's not good with too many features. Too many fields can increase the number of false positives and false negatives. So reducing and using that analysis tool that Hugo was talking about to narrow down the groups of fields in your model will help you to optimize it. And then vulnerable to overfitting. Sometimes if you build your model and the data that you're working with is more in a boundary of values, and then you have something new coming in that's outside that boundary, the logistic regression doesn't know how to accurately predict it. And that's the term that we use called overfitting. We built the model too good, I guess, that's how that would work. Poor performance when independent variables are not correlated to the target variable. So that's it, everyone. Logistic regression, linear regression. We've reached our port of call, and we have now ended hour 2. Remember, there is a link here where you can go out and get all that code that Hugo was demonstrating and the slides, of course. And if you need to contact us personally via email, here's our email addresses. So in closing, I just want to thank you for attending. I hope you enjoyed this session, and we will see you tomorrow morning for hour 3 of our machine learning travels. All right. Thank you, everybody.